Hello, everyone, and thank you for joining. Today, I'm going to talk about the GrAPL'22 C++ API. And specifically, I'm going to talk about a part of the API that we're very excited about, which is providing iterator support for our sparse matrix data structures. So, as all of you are probably familiar, GrAPL'22 provides a uniform API for implementing graph algorithms in the language of linear algebra. And what this means is exposing sparse matrix and vector data structures and operations. And this includes primarily for computation operations that can use arbitrary semi-rings instead of classical plus and multiply for matrix, matrix multiply, and matrix vector multiply. But it also includes a bunch of data munching operations for modifying data, putting data into data structures. And that's kind of what we're targeting with the Iterator API. So while most of the work to this point has been done in the C API, and it offers great portability, it has some disadvantages. We've been really focusing on the C++ API over the last 1 year to year and a half, and there are a number of different ingredients that go into the C++ API. I'm just going to talk about one of them today, which is the actual matrix data structure, and the kind of iterators that we want to build into this data structure in the API. So let's first talk very briefly about what a GrAPL'22 matrix data structure is and how you could control one. So in the reference API that we've been building, there is a GRB matrix class, which then has template parameters that users can use to control how the class works. First of these is defining the type of the stored values, and then the type used to store the indices. This could be int, it could be an unsigned integer, it could potentially be a big int class that behaves like an integer if you have really, really big indices. But allows you to kind of control how much memory you're using and what the range of values that you would support is. And then finally is a compile time hint about the storage format that would be used. And the kind of inspiration behind this is we want to enable developers to implement all kinds of different crazy backend sparse matrix data structures that could enable high performance for particular applications, and then to expose those with a combination of compile time hints that users can give. And what this would result in is essentially, depending on the implementation, having a different sparse matrix data structure that backs this generic sparse matrix representation, the sparse matrix API that you have. So, for example, as we have here, you might have one matrix, right, which represents a series of stored values. How those would actually be stored in memory is some kind of a data structure. One of the most common ones here, CSR, would split this up into row pointers that point to the beginnings of each row, along with column indices that correspond to each value, and then the actual value itself. And so most formats are going to separate the values and indices in some way. And each format may have a unique way of referencing these. Some may not even store some of these values. For example, if you have a dense matrix, that would just be a dense representation plus a bitmap of which elements are there. The indices may not exist anywhere in memory. So let's talk about what a GrAPL'22 matrix is from the user's perspective. From my perspective, there are three kinds of things you can do with a matrix. First, you can access the matrix metadata, which includes data about how many dimensions you have, the number of stored values there are, perhaps how much memory it's taking up, stuff like that. You can access individual elements through pointwise operations, like find to see if an element exists in your set of stored values, insert to insert a new element, and then you can also iterate through all the values. And that's what we're talking about today. So iteration is supported by C++ through all of the standard C++ STL data structures that people are used to. And so the way that this works is that there is a uniform API, which defines a range of values between the beginning of the data structure and the end, which is one past the last value. These are essentially modeled off of pointers, right? And so we can have an iterator, which iterates through every single value in the data structure. And then we can dereference that to get the actual value and then sum them all together. And the key here is that we can write this code once and then use it with many different containers. And indeed, we can achieve automatic parallelism and vectorization by using algorithms. So just by making a small change to this code, we can change this from being an std vector to any kind of container. What we've just done here is turned the type of the container, capital C, into a template parameter, and then done a little bit of template magic to figure out what the type of values that we are reducing is. And then we can change this vector thing here to some other type. So we could be summing all of the values in a set, for example. And indeed, we can modify this code to call a standard algorithm, right? There is actually a standard algorithm called reduce, right, which takes in the beginning of a container, the end of a container, and then performs a sum over all the values. And then one of the advantages of using one of these standard containers is that we can pass in an execution policy that defines how that algorithm should be executed. Here we pass in the parallel unsequenced policy, which tells the C++ runtime or the C++ library that this can be executed in parallel and also vectorized. So for generic sparse matrix iterators, these need to support a variety of different sparse matrix formats. So these, strictly speaking, are going to be different types depending on the hints that are given at compile time by the user. They could end up having corresponding to a different backend storage format. Then we're going to have a 1D iteration over the stored values. And each iterator is going to need to implement an increment operation, which will increment to the next stored value, and then possibly additional operations such as decrement and then randomly accessing. So in general, when we're building an iterator, the iterator needs to be able to point to a particular element. We need the ability to compare those iterators to see if one iterator is equal to another. And then we need the ability to increment the iterator to go on to the next element, and then possibly additional things depending on the type of the iterator. So if it's a bidirectional iterator, that simply means you can go in both directions. You can decrement it to go to a previous element. If it is a random access iterator, that means you can go to a random offset, similar to a pointer. So let's look at how some of the sparse matrix iterators have been implemented in our reference implementation of GrAPL' that I've been working on. So a COO iterator that we looked at is a potential CO iterator that an implementer could implement. It consists of essentially a reference to a series of matrix tuples. And then we also store a index, right? And that index is the specific number or the specific index of the tuple that we're pointing to. We can then fairly trivially implement two different functions, right? There's an increment function, which simply increments the index that you're pointing to. And then there's an offset function, which changes the index you're pointing to by a random offset passed in by the user. And so that's very simple, right? That's kind of a naive random access iterator. It is, very suitable for the COO data structure. For CSR, it's a little more complicated because we actually have two things that indicate which element we're pointing to. Now, one of those is a simple index, an index within the values array and within the column indices array that points to the particular element that we're accessing. However, because the row that we're pointing to is not actually written in memory, it's actually an integer, which is basically an index in the row pointer array. We have to perform some additional logic whenever we increment the CSR iterator. So we can trivially increment this index, but then we have to fast forward to find what row we're on next, right? Because there could be many empty rows separating two rows that have non-zeros in a CSR matrix. So that's what this fast forward row operation is doing. We also took a look at diagonal matrix format. I'm not going to show you the code for that, but it's actually quite similar to what we have here, except it's fast forwarding across multiple diagonals. Okay, so we implemented using this framework a generic sparse matrix multiply and a sparse matrix reduction. We'll take a look at the SPMM code really quickly here. What the SPMM code does is quite simple. There's one loop that iterates through all of the sparse values that you have. This is using the nice C++17 loop syntax. So we're iterating through every non-zero, and we're also destructuring that value into that tuple value into an index and a value. And then after we've extracted that index, we iterate through the rows of the dense matrix, and then actually do the element-wise multiplication. Now, again, the advantage of using this generic SPMM is that we can then compile versions of this that will be executed using a CSR matrix, a CSC matrix, a COL matrix, a DIA matrix, depending on the particular data structure. And so a user could potentially write code using these iterators, and then once a new data structure becomes available, they can then just recompile their generic code, and it'll be using that data structure. We compared these two implementations using raw pointers, and I'll go through this very quickly. Essentially, we iterate through the sparse matrix values, just as you normally do using a CSR matrix. Here it's 2 loops instead of 1 loop, because we essentially flatten these 2 loops by using the iterator. You iterate through the rows of the dense matrix after you've extracted those values from the CSR matrix data structure, and then you do the element-wise multiplication. So the key question we wanted to answer in this study is, how well do compilers do for generating code for the generic iterator implementation? So that is, what cost, if any, do we pay for using the generic iterators over using the raw pointers? And these two codes, as far as the code that's actually generated is concerned, are functionally equivalent. They're doing the same thing, but some of them, such as CSR and DIA, are restructuring the code and flattening them into one loop, and putting some of that loop code inside of the iterator. And so the question is the compiler going to be tripped up? And is it going to prevent things like vectorization and other compiler optimizations that improve performance? So in our evaluation, we looked at matrix reduction and at sparse matrix multiply. And we compared our generic C++ GrAPL'22 implementations in my reference implementation with compiled with hints to generate CSR, COO, and diagonal versions with raw pointer versions that just directly modify those data structures using raw pointers, or directly access those data structures using raw pointers. So what we found, we ran this code on Cori phase 1, single-threaded, compiled with GCC 10.0.1, which was the most recent compiler available on Cori at the time. And what we observed is that there is a slight performance loss for CSR and for diagonal. But that performance loss is generally within a few percent. Now, we did an assembly analysis, and a more comprehensive analysis is in the paper if you're interested. But we essentially looked at the assembly for each of these implementations. And what we saw is that the dip in performance for the CSR and DIA data structures was due to a failure to vectorize the code. So essentially, we flattened these loops, and that kept this version of GCC from vectorizing, at least vectorizing as effectively. Essentially, it caused spills, and then it ended up introducing more loop logic and branches. We did observe anecdotally, although we didn't do the same full experimental analysis, that with more recent compilers like GCC 11 and Clang, this is running on a different system, they were able to vectorize more efficiently, and that we didn't see the same performance drop. So we think that by essentially carefully organizing our data structures, we're going to be able to, and by using modern compilers, there should be a very low cost to using these iterators. So in terms of future work, one of the things that we've been thinking about is whether to provide ways to iterate through the matrix in a more structured way. For example, iterating by row, by column, or by diagonal. Not every sparse format can efficiently support each of these iteration methods, and so we would need to use range adapters and to try to make that cost evident to the user in some way. The other thing that I think is really important here is doing a more thorough performance analysis, particularly with C++ algorithms, because algorithms have the ability to give us better performance and to give us automatic parallelism using tools like Sickle and other parallel algorithms. So that's an overview of the Iterator API that we've been working on in C++ and some of the performance impacts.